Alright, this is a review on rework problems. Well, rework usually is a add-on to the problems we have already seen, mostly in a process analysis kind of problems, but rework can also be used in a little slow kind of problem, even waiting time calculations. In our class we'll see mostly on process analysis kind of problems. It'll come in two flavors. Let me go through the both. The first problem is, so consider there's a four-step assembly operations with quality problems, and the first resource processing time is 4 minutes, second is 3 minutes, the third is 5 minutes, and the fourth is 2 minutes. If that were, as we do in the process analysis problems, we first make the process flow diagrams. So let's do the same. Call this step 1, 2, 3, and 4. The processing times. The first step is 4 minutes per unit. The second one is 3 minutes per unit. The fourth one is 5 minutes per unit. The fourth one is 2 minutes per unit. Well, if there was no rework problems, this would have been an easy problem. With the processing time we could calculate the capacity, and the one with the lowest capacity would be our bottleneck. But that's not the whole story, because there is rework and scrap going on. So here there is a scrap of 50%. That is, out of everything he does, 50% goes scrapped. And in this step, 30% has to be reworked. So 30% of the work he does has to be reworked. So this brings complexity to our problem. How do we handle that? Well, the first step is do as we'd have done if there was no rework or scrap, that is, calculate the capacity. The capacity is 1/4 units per minute, 1/3, I'm not going to write the units again, 1/5, and 1/2. Now, to account for this rework and scrap, the technique we use is the one we had earlier. We've introduced this idea of implied utilization. We'll use the idea of implied utilization that we introduced in our second chapter. So the logic is, assume there is a demand of D, or another way to think of it is, assume the process is producing D units. If the process is producing D units, this guy has to work, the fourth guy has to work on D units. There is no scrap, there is no rework. The third guy has to work on 1.3 units or 3D units, because 30% of the units he has to work it again. So extra 30% he has to work. For every 100 parts produced, he has to work on 130 parts. Every 1 part produced, he has to work on 1.3 parts. This guy's a little tricky. Every 2 parts he produced, only 1 ends up at the final production. So for every D units produced, he has to work on 2 D units. Similarly, this guy has to work on 2 D units. This is the hardest part of this rework problems. After that, it's pretty straightforward. After we have that, so this is demand. Now we calculate implied utilization. The formula for implied utilization is demand over capacity. Demand is 2D divided by the capacity 1/4. This is 8D. Demand is 2D divided by the capacity of 1/3. This is 6D. Demand of 1.3D divided by 1/5 is 6.5D. Demand of D divided by the capacity of 1/2. This is 2D. So, unlike capacity, the one with the highest implied utilization is the bottleneck. So the step 1 is our bottleneck. So we have answered the second question. We have already answered this first question too, actually. For every unit of demand, how many units have to flow through the third step? Well, for every D units, you have to work on 1.3 D units. That means for every 1 unit, step 3 has to work on 1.3 units. What is the process capacity? Now that is a little tricky. As we know, the process capacity is going to come from the bottleneck. In this case, the bottleneck we know is step 1. But the answer is not so obvious. Otherwise, if there was no rework and scrap, we would have said, well, the bottleneck's capacity is 1/4 units per minute. That's why the capacity of the process is 1/4 units per minute. But that's not actually true here, because every time he works on 2D units, only D units gets produced. That means every time he works on 1/4 units, only 1/4 divided by 2, that is 1/8 units get produced. That's why the process capacity is 1/8 units per minute. Another way to think of this, to make the calculation a little easier, is 1/4 units per minute is same as saying 15 units per hour. Right? The relationship is 2D. The relationship with the output is 2D. So 2D equals to 15. So D equals to 7.5. So this is units per hour. 7.5 units per hour. You could have done the same here. The relationship is 2D for 1/4. That is D equals to 1/8. Either answer is fine. Units per minute or 7.5 units per hour. That's all there is to this kind of rework problems. A slightly difficult looking but not really that difficult problem, and this builds into the little slaw problem, but I'm not going to ask you anything related to the little slaw, but the ideas are exactly the same. In this problem there are two steps. One is an ICU, the next is the cardiology ward. So the story here is, you go ahead and the story here is, consider the following situation: the cardiac ICU in a large hospital, patients admitted to the ICU, and then they go to the they stay there on average for 5 days. However, this assumes that the patient do not develop any complications. 20% of the patients develop complications in ICU, and they stay altogether 13 days in the ICU. After they are discharged from ICU, they are moved to the cardiology ward. Here they spend for 4 days, assuming no further complications, but 5% patients develop complications and they are readmitted to ICU. And in this, they spend additional 13 days in the ICU. They come back to the ward, the cardiology ward, and spend another 13 days. And we'll come back to this 12 beds in ICU and 18 beds in ward. So what's happening? What is happening here is, there is ICU and there is cardiology ward. In this, on average, people stay there for 5 days. Right? People stay there for 5 days. 80% of the people just move on. Right? 80% of the people move on to the cardiology ward. But 5% people, instead of moving, 20% of the people, instead of moving on, have to stay there for another 8 days, making it altogether 13 days. So they have to stay there for another 8 days. Right? Now, what happens at the cardiology ward? At the cardiology ward, people stay there for 4 days, and for 95% of the people, that's good, and they go home. But 5% of the folks, they have to be sent to the ICU. Right? And these people stay in ICU for another 13 days. Right? And they come back and they stay in cardiology ward again for 4 days. So these people again have to stay here for 4 days. A lot of pictures, but if you draw it yourself, they will make sense. So the question is, on average, how much time an average patient will spend in the ICU? Alright, let's figure this out. On average, at ICU, let's not worry about these patients yet. Let's only worry about the first time staying there, and then there's those 20%. So what's happening there? All 100% of the patients, right? 100% of the patients first stay there for 5 days, right? And then there's 20%. This 20% stay there for another extra 8 days, right? So on average, the patient stays in just this portion is 1 multiplied by 5 plus 0.2 multiplied by 8 days, which is 6.6 days. But that's not the whole story, because these patients also demand the ICU's time. So how many of them are there? Only 5% of them are there, the total, and they spend 13 days, right? So we have another 5%, 0.05, that needs service of another 13 days. So altogether we have 6.6 days plus, for this 5%, 13, that is 6.6 days plus 0.65, making it 7.2 days. So on average, an average patient demands 7.2 days of the time at the ICU. Next question is, where is the bottleneck? Next question asks, where is the bottleneck? Well, to find where is the bottleneck, we need to find what's the capacity at the ICU, and we need to find what's the capacity at the cardiology ward. Let's find the capacity of the cardiology yard first. Let's find the how much time on average patient spends at cardiology yard first. Well, all 100% patient stays there for 4 days, right? Another 5%, which went there and came back again, those spent for another 4 days. That is 1 into 4 plus 0.05 into 4. So an average patient stays there for 4.2 days. So we know the processing time on average for the patient at the ICU is 7.2 days, and the processing time for average patient at the cardiology yard is 4.2 minutes. After that, we come back to, now our picture is very similar to our steps. So they call this a step A, call this a step B, and this has a processing time of 7.25 days, and this has a processing time of 4.2 days. Now let's going back here. We know there are 12 beds in the ICU and 18 beds at the ward. So there are 12 beds here. So it's just like saying there are 12 workers here, right? 12 beds here and 18 beds here. So the capacity here is 12 divided by 7.5, right? Here 18 divided by 4.2. So the processing capacity here is 1.6551 patients per day. Here it is 4.2857 patients per day. Right. That answers most of our question. This is 4. Alright, where is the bottleneck? Well, this has a capacity of 1.65 patients per day, and this has a capacity of 4.28. So this must be the bottleneck. That is, the ICU must be the bottleneck. Right? The next question asks, how many surgeries can the hospital perform per day? That is, what is the capacity of the process? If these were the only two steps. Well, this is the capacity of the bottleneck. So the hospitals can perform on average 1.6551 surgeries per day on average. That's all there is. It's just understanding what the question, translating what the question is saying in terms of words into numbers.